name's Chellie. I'm a third year PhD student in agricultural economics at Oklahoma State University. And so I'll go ahead and share my screen. Let's go to my presentation. All right, as long as everyone can see my screen, then we're good to go.
We can see a screen.
Perfect. All right, so today I'm going to talk to you a little bit about my research that I'm doing under the RAIN project, which is really focusing on applying some game theoretic approaches to try to identify optimal strategies to manage resistant weeds. And so this is a progress update, so it shouldn't go the full 45 minutes at all, but I think it'll give a good idea of kind of where I am in my research as it's related to RAIN. Oops, let's see here. There we go. So first, obviously acknowledge RAIN, NEFA, OSU, and K-State for being all involved in this collaborative research endeavor. So first, let's do an introduction kind of on how we arrived at this issue of having to deal with resistant weeds in our agricultural systems. So I think it really begins with the introduction of herbicide-tolerant crops that were introduced to the market in the late 1990s. So I have included a graph on your right-hand side that shows the adoption rates for herbicide-tolerant crops, soybean, cotton, and corn, and kind of how those adoption rates have increased over the years. And they've all experienced really quick adoption rates. And I think the quick adoption, at least in part, could be attributed to the fact that when a farmer implements these herbicide tolerant crops, they can implement a simpler, a low cost, while still highly effective weed management system. But nothing in the world is perfect, unfortunately. So the recurrent use of single herbicides has really increased to the selective pressure on weeds. So as this use of herbicide-tolerant crops have increased, so has the prevalence of herbicide-resistant weeds. So just kind of some figures to show kind of where they are and just kind of snapshots of how it's changed. On your left-hand side, there's a map from Zhu et al. In 2015. They did a survey trying to identify kind of hotspots of initial resistant weed infestations. And so the circles on the map kind of draw your eye to the hotspots, which right away it's very clear to see West Tennessee, Northeast Arkansas, that's been a problem area, Panhandle of Texas, Southern Georgia, and coastal North Carolina. And then on your right-hand side, I've pulled from the International Survey of Herbicide-Resistant Weeds. And this map is of the Eastern US, and it shows the number of glyphosate-resistant weed species identified. This is as of 2016. So again, right away, Mississippi's not doing too well. Tennessee's not doing too well. Missouri, Kansas, Arkansas, they're all having a lot of issues, but it's not just localized to the Southeast. It has spread up through the Eastern US. And so when it comes to thinking about this problem in terms of maybe what's the economic aspect of this problem is, so there are negative externalities that result from non-optimal control of weeds. And so when I say negative externality, I mean, as an example, if I'm a farmer and I'm planting a certain cropping system and I notice, there are weeds that are popping up and they're not really being controlled very well by my herbicide strategy, but I'm just going to keep doing what I'm doing. I'm just going to keep spraying the same thing, hope that they'll just go away. But through wind, water, through equipment transfer, these weeds are now transferred to my neighbor's field. And now they're having to increase their costs, change their strategies, incur other expenses. That's a problem that my non-optimal control has caused, and I'm not able to internalize that cost. So that's kind of what the negative externality means in this specific scenario. And so when we want to think about, okay, what's the dynamic between a producer and a weed? Both can be thought of as kind of players in a game where they're both kind of trying to outdo one another at each time period. So it's essentially an arms race. It can be thought of as an arms race. So for example, a producer uses a certain herbicide. Some weeds do die from it, but some survive. So those that survive are going to continue to mutate, continue to get stronger, better, faster. And then the producer is going to change strategy, try something else. The weeds are going to react and get better, stronger, faster if they can. So it's just kind of a never-ending one-upping each other. So ultimately, the frequency of that resistance trait is going to increase, which is not optimal in general. And so kind of a brief literature review. So a lot of papers have looked at this problem because it's not exactly a new problem. I mean, the 1996 was over 20 years ago now. But most papers have focused on estimating costs of herbicide-resistant weed management on a single farm. And there have been a few that have incorporated game theoretic frameworks to set up their problem, to think about the dynamics of their problem. Heal et al. In 2004, they had a two-farmer game of sorts where the farmers could cooperate or not cooperate in terms of crop mixes to try to reduce infestations of weeds on their farms. And then Grimsrud in 2007 looked at cattle pastures and yellow star thistle and how each neighbor could select optimal strategies given the infestation levels on their neighbor's fields. And then Richards et al. Looked at invasive bufflegrass, I believe that's how you pronounce it, in Arizona, and tried to identify, neighborhood strategies, coordination strategies to try to reduce or eradicate the presence of bufflegrass. So the objectives of this research that I'm doing is kind of building off previous ones and continuing the game theoretic aspect. But it's to apply game theoretic frameworks and ideas to identify optimal strategies to address these market inefficiencies caused by herbicide-resistant weeds, specifically in rain-fed agricultural systems. And so I think more specifically, it is to determine optimal strategies, which include alternative cropping systems such as double cropping to manage herbicide resistance on a single farm. And so kind of graphically, what this means is that, so you have your non-resistant weed population, and that is defined by the red curve. And you have your resistant weed population, and that's defined by your black curve. And so over time, we see a decrease in the level of non-resistant weeds, but we see an increase in the level of resistance due to mutation brought about by, recurrent herbicide or herbicide that's not working on the weeds themselves. But we have this point, especially with non-resistant weeds, where they are at least more manageable than resistant weeds. There becomes a point when the weed population, as it becomes dominated by resistant weeds, it does become less manageable. So that's why I put in the blue crop curve, which signifies that over on the far left-hand side, when non-resistant weeds are, they're still high, but manageable, we aren't getting too much of a crop yield penalty. It's not really damaging our crop too bad. But as we move down the crop curve, as resistance increases, that's when we start to see more penalties. So overall, this research is really hoping to identify cropping systems that essentially bend that resistant curve down. Just keep it lower. We don't really want it to get as high as it possibly could, where it really does continually damage our crop. And so how do we answer that question? Well, we have to simulate some data and generate some data first. So we are looking in rain-fed cropping systems that are prevalent in the Great Plains. So we've identified 3, the first being a wheat fallow rotation, the second being a wheat sorghum rotation, and the third being a wheat soybean rotation. And so all of these cropping systems are simulated using the agricultural land management alternative with numerical assessment criteria. The acronym is Almanac, which makes it a lot easier to say. And so all of these cropping systems were simulated for an El Reno, Oklahoma location because we are benchmarking our yield data on El Reno trials. So soil data is from Surgo from the El Reno location. Weather is from a NOAA weather station nearest El Reno, Oklahoma. And so with our crops, we obviously had to choose some weeds to also simulate to create that competition of crops versus weeds. And so we picked 2 weeds that are in the area or in the Great Plains, Southern Great Plains area. The first is Palmer amaranth, which is also known as pigweed, and it's a summer annual broadleaf weed in the Southern Great Plains. It's exhibited resistance to 8 modes of action. And then the second is mare's tail, which is also known as horseweed. It's a winter annual herbaceous weed, also in the Great Plains. It's also exhibited resistance to 8 modes of action. So both of these weeds can be very problematic in fields, especially at high infestation levels, because it's been documented that both cause yield penalties of greater than 60% when they are at high infestation levels. So these are very problematic for rain-fed cropping systems. And so cost of herbicides are gathered from Oklahoma State crop budgets. Prices for these soybeans, sorghum, and wheat are gathered from the Food and Agricultural Policy Research Institute. So they do 10-year forecasts based on market indicators and things like that. So I just pulled the next 10-year forecast down from that. And so we've simulated our cropping systems, our wheat fallow, wheat soybean, wheat sorghum, and we've simulated them under 3 different tillage systems. So the first being a conventional tillage system, the second being a no-till system, and the third being a mixed till system. And so here's some management information that I had to put into Almanac, obviously to get it to run and to simulate a cropping system that would be found in Oklahoma. So with nitrogen rates, phosphorus rates, things like that, Almanac comes with suggestions for what those levels should be. You can use those suggestions or you can alter them, putting in recommendations for the area. And then you can look at your Almanac output and it tells you if there was any nitrogen stress days, any phosphorus stress days, anything like that. So you can kind of tailor a little bit to make sure that your fertilizers are being applied as they should be. And so this is for wheat fallow, wheat soybean, and wheat sorghum. That's pretty much it with management. So when I initialize the crops in Almanac, I also have to initialize the weed populations. And so we needed to designate some kind of low, medium, high levels of weed infestation initially in a field. And so I had to initialize 4 separate populations of weeds, if that makes sense. A palmer amaranth, then I had to initialize a resistant palmer amaranth, so one that would not be susceptible to herbicide applications, a horseweed, and a resistant horseweed. So I got these levels from literature, and I worked with one of my committee members, Dr. Manucheri, to kind of get these delineations correct for this specific problem. And so I've included some simulated yields from the wheat sorghum runs. And so I've included a best case scenario and a worst case scenario just to kind of orient the simulation. The very bottom row is going to be the best case scenario where I did not initialize any weeds. This is just, if we could have a weed-free world, what would yields look like based on the input data that I have. And so the top row is the worst case scenario. So that's we're not going to try to control the weeds. We're just going to initialize the population and we just let it grow. So there is that yield penalty of, looking at wheat going down from 48 bushels per acre in our best case scenario to 15 bushels per acre in the worst case with no control. And so when I compare this with a wheat fallow rotation, so when the do nothing scenario of the wheat fallow, it produces a lower wheat yield, which I think follows with some of the literature that I've read, in that planting a summer crop can help you manage weeds with the rates to canopy and kind of the controlling the resources with a crop you actually want there instead of weeds which you don't want there. And so kind of looking at this graphically, because graphs are always much nicer to look at than just numbers. So on your y-axis, I have biomass, and on your x-axis, I have years. This is a 35-year simulation. And the top graph you see is of low herbicide-resistant population. And this is for a wheat fallow no-till scenario. And so as we can see, the red line is the total weed biomass. So it's there. It's not that it's not there, but it seems pretty constant. And your wheat biomass, it is still growing higher than your weed biomass. So the wheat is still controlling more resources of the field, and it's not being penalized too much by the weed population. But the lower graph is your high herbicide resistance population scenario. And you can see the total weed biomass, it increases very quickly, and it has a slight upward trend going through time. And the biomass is greater than the wheat biomass. So there are bigger yield penalties in this high resistance scenario when compared to the low resistance scenario. But I think I want to point out from this graph, perhaps a bigger point, which is that you can see that there's this clear dynamic, and you have these rises and falls of populations, and it's kind of a cycling effect. And so when it comes to modeling this problem, we really need to try to capture this cyclicality of these populations. And one way to do that is to use a Lotka-Volterra predator-prey model that characterizes two populations kind of fighting against each other for control of resources. And so again, this predator-prey idea of, this is a game. It can be thought of as a game because you do have these kind of battles going on with your predators and your prey. So from this data, to answer that big overall question of how can we kind of bend that resistance curve down, I need to get two things out of this data. I need to find out the probability of an infestation changing from one level to another, given a cropping system is used and given some level of effort that is expended towards controlling weeds. And I need to figure out how the weed population damages the yield. I really need to define that relationship so I can actually see what the outcomes are. And so in terms of the probabilities, why do I need these transition probabilities? And it's because the overall problem is stochastic. So we really have to model that uncertainty that a producer faces in terms of these changing weed infestation levels. And so from the data that you've used to create that graph, I can calculate these transition probabilities. And I'll walk through an example to kind of show how these read. So we'll pick this bottom right square, which this was created from a wheat fallow rotation, mixed tilling system, low initial population density. So this low, medium, high, this first column, that denotes what level the field is in the current time period. And then your top row, this low, medium, and high on the top row, denotes the level of infestation in the next period. So how this reads is if I begin with in a low category, if I'm in a low level of weed infestation, there's a probability of 0.78 that I'll remain in a low infestation level for the next period. Moving across, if I again begin in a low infestation level, there's a 0.21 probability that I will move up to a medium infestation level by the next time period. And so you create 9 transition probability matrices per cropping system. So there's a total of 36 created for this problem. And so then the steady row I have on the bottom, this denotes the steady state transition probabilities, which this essentially says that these are the average probabilities that the system will be in a certain state after a large number of transition periods. So it's not saying that the system can't, transition from low to medium. It's just saying that these probabilities are going to hold after an X amount of steps. And so with these transition probabilities, we can kind of apply it to see kind of how these systems work over time. And so I just grabbed some revenue numbers. This is just made up these revenue numbers to kind of show the system dynamics and how these probabilities can work and how they look over time once you multiply them by your revenues 30 times. So at the top, we have a wheat fallow, low density, no till. So the dynamics, the probabilities kind of characterize these revenue dynamics. And then the wheat soy at the bottom is just another example of how it changes as we look across different systems. So every system would produce a different dynamics with respect to curves, if that makes sense. And so the second point that I said I needed to get from this data was I needed to somehow define a relationship between weed biomass and yield to try to characterize that damage. And so it really helps to just plot your data. I think that's like the first thing they teach us in school is just, you have your data, look at your data. It really helps to try to think about what kind of functional forms might fit it. So you're not going in blind. You can kind of have some prior understanding of maybe what you might want to try first. And so this is just a simple scatter plot. Wheat biomass is on your y-axis, weed biomass is on your x-axis. And so from this scatter plot, it kind of looks like maybe an exponential function. It might have a little curve downward. So there are two functions that I tried to estimate for these damage functions. The first is an exponential function, as I just mentioned, and the second is a power function. And so I've included the specifications. So the model 1 is an exponential function. And with that, the R squared is 0.71. The alpha is estimated to be negative, and the asterisk denotes that it is significantly different from 0. And it's behaving in a way that we expect, in that there is a negative relationship between total weed biomass and yield. And there is also, in the power function, it also shows that there is a negative relationship between weeds and yield. So again, both of these are as expected. I just went with the R squared for today. So with the highest R squared, we went with the negative exponential model. And so when I add those fitted values in, which are the red crosses right here, you can see that there is kind of that negative relationship that starts to flatten out towards the end. So there are several other kind of yield functions that we can try and that we will be trying moving forward, just to see if we can maybe get a better fit. And so all of this kind of comes together into a stochastic dynamic programming problem setup. And so stochastic dynamic programming is used to determine optimal decisions for various agricultural activities. And so what it does is it breaks the problem down into these sequences over time, these sub-problems. But for this problem specifically, we need to think about how to set the stochastic dynamic program up, because we have, over time, we have these specific actions occurring at different points in the year. So you harvest, and then you have to choose maybe a summer crop, then you harvest a summer crop, you plant wheat, you harvest, you choose a different summer crop. So there's all these options, but then you also have these, in-season decisions that you also have to make regarding management, such as weed management, such as herbicide use. So when it comes to setting it up, it's really difficult to try to incorporate these in-season effects and these across-season effects. So it's kind of a complicated problem setup. And so that's kind of where we're at in terms of progress with this thing, is we've got the conceptual laid out, and we're really working to get it all together to make it run smoothly. But the next steps would be to obviously estimate yield damage curves for soybean and sorghum. The second is to parameterize weed growth equations, which will govern kind of that yield penalty. The third is then to link all the damage curves with the decision-making problems. And then the third, point A, is to add in-season herbicide decisions that should affect your weed growth and your weed levels. So that's it. So thank you for your time. And if you have any questions, I can try really hard to answer them.